I'm Paria Rasouli, a PhD student and a pharmacist from UCL in Belgium, and I'm very glad to be here today to talk about my thesis project. So the title of this poster is a pharmacological evaluation of a newly designed potentiator of antibiotics against gram-negative bacteria. Why gram-negative bacteria? Well, there is an emergence of antimicrobial resistance through this last decade, and especially caused by gram-negative bacteria such as Pseudomonas aeruginosa. And so, the reason of a non-response for our current treatments is multifactorial. But one of the reasons behind that is that in gram-negative bacteria, we have a double-layer membrane causing poor antibiotic penetration into the cell. So one of the strategies might be to destabilize this bacterial membrane, and by destabilizing we can have higher antibiotic accumulation into the cell. And this is exactly what we are doing with our groups and with the help of Marseille University. And with the design of something that we called potentiator, which is called GS238, we have a higher gain in the activity of several different classes of antibiotics. Most of them are poorly permeable drugs, which it means that they are not active against Pseudomonas aeruginosa. And so, with a big screening step, we have selected GS238, which is a potentiator and not an antibiotic, which means that this compound has a little antimicrobial activity by itself, but is with the help of the antibiotics that we can enhance their activity. And so, first thing that we have observed is that we can have a reduction in the MIC of 6 different classes of antibiotics, 5 of them that are poorly permeable drugs. To go further, we also wanted to understand and characterize the mechanism of action of GS238, and so for that we have done 4 different assays. The first one was a binding assay to understand its binding to the outer membrane of the bacteria, and so for that we have done some body pile cadaverine displacement assay, and we have noticed that higher concentration of potentiators leads to higher body pile cadaverine displacement, and so higher binding to the LPS of the outer membrane in the bacteria. And to go further, we also wanted to understand how the potentiator works on the outer membrane, how it permeabilizes. And so for that, we have done some permeabilization assay by using vancomycin FITC and some antibiotic accumulation assay by doing some rifampicin FITC. And so, for both assays, we have observed that higher concentration of potentiator we use, higher permeabilization we observe, and so higher antibiotic into the cell we observe also. And finally, we have also done some membrane packing assay. And so this membrane packing will tell us how the lipids are rearranged in the outer membrane of the bacteria. And we have observed that we have less membrane packing, which means that in the presence of the potentiator, we have also a decrease in the membrane packing, so a looser membrane, which can also allow the antibiotics to penetrate better into the cell. And so, from this poster, what we have observed up to this point, well, first we have observed that we have a reduction in the MICs of different classes of the antibiotics with the help of our potentiator, and that for its mechanism of action, we can say that it binds to the LPS of the outer membrane, it permeabilizes the outer membrane, and by doing that, we have higher antibiotic accumulation into the cell. Of course, I would like to conclude that we have a lot of work to do, and this is the first point, but we have to also characterize it better and to understand better its mechanism of action. And now I would like to conclude by saying that I hope that with this kind of strategy we will do the use of some antibiotics great again, and thank you very much for your listening.